Hi everyone and welcome to this video on transaction processing. It's part of the A-level computer science curriculum and today we'll be covering Unit 4, Exchanging Data, focusing on how data is captured, managed and processed in databases. We'll also dive into some key concepts like ACID principles, record locking and redundancy. So by the end of this video, you'll have a solid understanding of these topics. So let's get started. In this video, we'll cover the following objectives. We'll explore different methods of capturing data, both manual and automated, and look at real-world applications for each. We'll discuss how data is input into databases and the role of Electronic Data Interchange, EDI, in exchanging data between systems. We'll explain what transaction processing is and why the ACID principles are so important in maintaining database integrity. We'll also look at record locking and why it's necessary in multi-user databases. Finally, we'll talk about redundancy and how it helps ensure system reliability. Let's start with data capture methods. Before data can be used, it needs to be captured. There are several ways to do this, and I've listed some examples here. For instance, manual data entry involves typing data from handwritten forms into a system. Think of a receptionist entering customer details from a sign-in sheet. On the other hand, automated methods are faster and more efficient. For example, barcode scanners are used in supermarkets to quickly scan products at checkout. Smart card readers are used in offices to grant employees access to secure areas. Sensors can monitor environmental conditions like temperature in a greenhouse. Each method has its own applications, and choosing the right one depends on the situation. Once data is captured, it needs to be input into a database. This can be done in several ways. Automatically using database management software, manually by typing data into custom forms, importing data from spreadsheets or files, using Electronic Data Interchange, which allows computers to exchange documents like invoices or purchase orders. For example, imagine a retailer sending an electronic purchase order to a supplier. Instead of mailing or faxing the order or faxing the order, they use EDI to send it directly to the supplier's system. This saves time and reduces errors. Now that data is in the database, how do we retrieve it? This is where SQL comes in. SQL, or Structured Query Language, is used to select data that meets specific criteria. For example, if you wanted to find all customers who live in London, you could write an SQL query like select from customers where city equals London. This query selects all records from the customers table where the city column equals London. You can also use tools like Query by Example in database software to visually build queries without writing SQL code. The selected data can be used for reports, mailing labels, or even printing barcodes. In databases, a transaction is a single logical operation that may involve multiple steps. For example, when you book a flight online, the transaction might include checking seat availability, processing your payment, issuing your ticket. All these steps must be completed successfully for the transaction to be valid. If any step fails, the entire transaction should be cancelled. But what if the system crashes after updating the seat availability, but before processing payment? This is where the ACID principles come in, which we'll discuss next. ACID stands for atomicity, consistency, isolation, and durability. These principles ensure the database transactions are processed reliably. Atomicity means that a transaction is treated as a single unit. It either completes entirely or not at all. For example, if a payment fails, the entire transaction is rolled back. Consistency ensures that data remains valid before and after a transaction. For instance, a bank transfer must not leave an account with a negative balance. Isolation ensures that concurrent transactions don't interfere with each other. Imagine two people trying to book the last seat on a flight at the same time. Only one can succeed. Durability guarantees that once a transaction is completed, it remains permanent, even after a system crash. These principles are crucial for maintaining database integrity. In a multi-user database, multiple people can access and update data simultaneously. This can lead to problems such as lost updates. For example, imagine two users updating the same customer record. User A changes the customer's phone number. User B updates the customer's email address. If both users save their changes at the same time, one update might overwrite the other. This is where record locking comes in, and we'll discuss this next. Record locking prevents multiple users from accessing the same database record simultaneously. When a user retrieves a record for editing, it's locked until the transaction is completed or cancelled. For example, imagine a librarian updating a book record while another librarian tries to edit the same record. With record locking, the second librarian would have to wait until the first one finishes. Without record locking, updates could be lost, leading to inconsistent data. While record locking is useful, it can lead to deadlock. This means when two users are waiting for each other to release locks, causing a standstill. For example, user A locks record 1 and waits for record 2. User B locks record 2 and waits for record 1. Neither can proceed, and the system gets stuck. To prevent this, databases use serialization techniques, which we'll discuss next. Serialization ensures that transactions are processed in a sequence, preventing interference or lost updates. Two most common techniques are timestamp ordering, where each transaction is assigned a timestamp, and conflicts are resolved based on the order of timestamps. Commitment ordering. Transactions are ordered based on their dependencies and initiation time. For example, if two users try to update the same record, the system will process the transaction with the earlier timestamp first. Let's talk about redundancy. Many organizations, like banks or airlines, can't afford system downtime. Redundancy ensures reliability by duplicating hardware and data. For example, an online banking system might have backup servers in different locations. If the primary server fails, the backup takes over automatically, ensuring uninterrupted service. To recap, so far in this video, we've covered methods of capturing, selecting, managing, and exchanging data, transaction processing and the ACID principles, record locking and its importance in multi-user databases, redundancy, and its role in system reliability. Let's move on to the second part of this lesson. And let's take a closer look at manual methods of data capture. This involves entering data by hand, often from paper forms. For example, imagine a receptionist typing customer details from a sign-in sheet into a computer system. While this method is straightforward, it can be time-consuming and prone to errors, especially if the handwriting is hard to read. On the other hand, automated methods are much faster and more efficient. These include smart card readers, like those used in offices to grant employees access to secure areas, barcode scanners, which you've probably seen in supermarket checkouts, OCR, or optical character recognition, which converts printed text into digital format. Think of scanning a book to create an e-book. Sensors, which can monitor things like temperature or humidity in real time. These methods reduce human error and speed up data entry. Now, let's talk about Electronic Data Interchange, or EDI. EDI is used to exchange business documents like invoices, purchase orders, and shipping notices between companies. Instead of sending paper documents through the mail or fax, EDI allows computers to communicate directly. For example, a retailer might send an electronic purchase order to a supplier. The supplier's system automatically processes the order, updates inventory, and sends back a confirmation, all without any manual intervention. This saves time and reduces errors. Once data is in the database, we often need to retrieve specific information. This is where SQL, or Standard Query Language, comes in. SQL allows us to write queries to select data that meets certain criteria. For example, if we wanted to find all customers who live in New York, we could write a query something along the lines of select from customers where city equals New York. Now, just to recap, we have an asterisk after the select, because then we can select all the fields in the database. And then the city is where we will narrow our search down to New York. So this query will select all the records from the customers table where the city column equals New York. You can also sort the results, filter by multiple conditions, or even join data from different tables. SQL is a powerful tool for working with databases. Let's look at a real-world example of transaction processing. Imagine you're booking a flight online. The transaction might involve several steps, such as checking if seats are available, processing your payment, issuing your ticket. All these steps must be completed successfully for the transaction to be valid. If any step fails, for example, if the payment doesn't go through, the entire transaction should be cancelled. This ensures that the database remains consistent. Now let's dive deeper into the ACID principles, starting with atomicity. Atomicity ensures that a transaction is treated as a single unit. It either completes entirely or not at all. For example, imagine you're transferring money from one bank account to another. The transaction involves two steps: deducting the amount from the first account and adding the amount to the second account. If the second step fails, the first step should be rolled back. Otherwise, you'd lose money. Atomicity ensures that both steps are completed together or not at all. Next, we have consistency. This principle ensures that data remains valid before and after a transaction. For example, a bank transfer must not leave an account with a negative balance unless it's an overdraft account. Consistency is maintained through validation rules, defined when the database is set up. These rules ensure that data always follows the correct format and constraints. Isolation ensures that concurrent transactions don't interfere with others. Imagine two people trying to book the last seat on a flight at the same time. Without isolation, both transactions might succeed, leading to overbooking. Isolation ensures that transactions are processed one at a time, as if they were happening sequentially. This prevents conflicts and ensures data integrity. Finally, durability. This guarantees that once a transaction is completed, it remains permanent, even after a system crash. For example, if you book a hotel room online, the booking should still be valid even if the system crashes right after you confirm it. Durability is achieved by saving transaction data to a secure storage medium, like a hard drive, before the transaction is considered complete. In a multi-user database, multiple people can access and update data simultaneously. For example, imagine a travel agency where several agents are booking flights for different customers at the same time. This can lead to conflicts if two agents try to book the same seat. That's why mechanisms like record locking and serialization are so important in multi-user databases. Let's look at an example of record locking. Imagine a library system where two librarians are trying to update the same book record at the same time. With record locking, the first librarian locks the record while making changes. The second librarian has to wait until the first one finishes. This prevents conflicts and ensures that updates aren't lost. However, record locking can lead to deadlock. This happens when two users are waiting for each other to release locks. For example, user A locks record 1 and waits for record 2. User B locks record 2 and waits for record 1. Neither can proceed and the system gets stuck. To prevent this, databases use serialization techniques, which we'll discuss next. Serialization ensures that transactions are processed in a sequence, preventing interference or lost updates. Two common techniques are timestamp ordering, where each transaction is assigned a timestamp, and conflicts are resolved based on order of timestamps. Commitment ordering. This is where transactions are ordered based on their dependencies and initiation time. For example, if two users try to update the same record, the system will process the transaction with the earlier timestamp first. Finally, let's talk about redundancy in practice. Many organizations, like banks or airlines, can't afford system downtime. Redundancy ensures reliability by duplicating hardware and data. For example, an online banking system might have backup servers in different locations. If the primary server fails, the backup takes over automatically, ensuring uninterrupted service. So again, let's recap the key concepts we've covered this lesson. Methods of capturing, selecting, managing, and exchanging data. Transaction processing and the ACID principles. Record locking and its importance in multi-user databases. redundancy, and its role in system reliability. These concepts are fundamental to understanding how databases work in real-world applications. That brings us to the end of this video. I hope you now have a clear understanding of transaction processing, ACID principles, record locking, and redundancy. These concepts are essential for working with databases and ensuring data integrity. If you have any questions, feel free to leave them in the comments below. Don't forget to like and subscribe for more educational content. Thanks for watching, and I'll see you in the next video.